This is section 1.3. It's a video about cardinality, which informally means the size of a set S. Now, you might expect that infinite might count as a size, so that those infinite sets that we met a few sections ago would all count as the same size. But in fact, it's more interesting than that. There's a definition of cardinality, which we're going to see in chapter 3, under which the naturals, the integers, and the rationals all have the same cardinality, but the reals, that set has a different cardinality. It's a different size, if you like, which is maybe surprising. There's this definition of cardinality for infinite sets that has subtle distinctions between different infinite sets. Unfortunately, we have to start with finite sets, so I'm going to delay any discussion of the size of an infinite set until we get to chapter 3, and just in this video we're going to work with finite sets and a recursive definition of cardinality. So we'll see a definition here, and then later on in section 3 we'll see a new definition that supersedes this one. It gives the same answer as the one we're going to see today, but the one later on uses some more technology that we get in chapter 3, which we don't need for finite sets. Here we go. So first I need to tell you what a finite set is, and to set the tone I've got a recursive definition of this. If you cast your mind back to the previous chapter with the natural numbers, you'll remember we had quite a lot of definitions with this structure, right? With two parts, a sort of trivial part and a general part that relates to previous things. That's for a reason, of course. So a set S is called finite if either it's the empty set, that one counts as finite, or if there exists an element of S such that the set difference S, take away that element, is a finite set. So that's a recursive definition because it invites you to subtract and investigate. It's not particularly useful for deciding whether sets are finite or infinite, because if your set is infinite and you try removing elements, the idea is that you will never get down to the empty set, but that's quite hard to prove. So this is quite a good definition if your set really is finite, and quite a hard definition to work with if it's not. I'm going to stick to finite sets today. So for example, the set that contains 0 and 1 is finite because the set that contains just 1 is finite because the empty set is finite. So I can remove elements and get down to the empty set, which is finite by part I of our definition. If that reminds you of induction, then all of these things are related, I suppose. Okay, any set that's not finite is infinite. And then I can define cardinality, and my definition of cardinality is related. It's written like this. I would say cardinality of S, or maybe just the size of S if I was in a hurry. It's a natural number, and it's defined as follows. If S is the empty set, then we say that the cardinality is 0. So I might write facts like this. The size of the empty set is 0. If S is not empty, but is finite, then by definition of finiteness, it must have been in the second case. So there exists some element of S such that when you remove that element, you get a finite set. And then my definition is going to be that if the size of that set, after you remove S, is the number n, then we define the size of this set to be n plus 1, the set including that element S that you removed. So this lets us build up from sets of size 0 to sets of size 1 and then 2 and then so on through all of the natural numbers. And it really relies on my definition of finiteness. If you try to do this for the set of natural numbers themselves, well, they're not finite. So if you try removing an element, then you won't get a finite set, and you won't have this if it's equal to n property. So I'm trying to build this up with some sort of recursive definition. Okay, that's the cardinality of this. It's not very practical, and I can't wait for chapter 3 when we get a more practical definition of cardinality. There's also, it's enough though that we can prove facts about cardinality, the size of the set, including things like this, that the size of a union B is the size of A plus the size of B minus the size of the intersection. So as a diagram, this is maybe A and B, and the size of the union would be the size of A plus the size of B, but then I've double counted all of the things in the middle, so minus the intersection. I'm afraid that doesn't count as a proof, and I'm afraid that the proof is left as an exercise on the problem sheet to use the recursive definition to build this up by, if you like, slowly increasing the size of one of the sets. We start by claiming that it's obvious for the empty set, following through all the definitions, and then building up the size of the sets from there. Because they're finite sets, you can do that to build things up like that. And at the moment, we only have cardinality for finite sets. We should probably not think about statements like that for infinite sets, in which case, I don't know, we're adding and subtracting infinities, which does not feel like something we should be doing. Anyway, I've wanted to put this on the screen because, as well as being on the exercise sheet, it's also a good fact. It's the start of something called the principle of inclusion-exclusion, which you might have seen before if you've done some sort of Olympiad counting problems, where you do those steps of counting and then realizing you've double counted and fixing it. And there's a principle which takes that further to what happens if you've triple counted, and so on. If you want to look that up, it's called the principle of inclusion-exclusion. If you like this statement but just wish it had more terms on the right-hand side and more sets A, B, and C. Anyway, the reason I've got it on the screen is that I want to tell you about, in particular, excuse me, let's tidy that up. In particular, if the sets are disjoint, then that cardinality on the end is 0. So the cardinality of the intersection is the cardinality of the empty set, which is the number 0. So the cardinality of A union B becomes just the cardinality of A plus the cardinality of B. They just get added together without worrying about the intersection, because that's empty. That's a fact that I would like to use in a quick proof that the cardinality of the power set is something that we can calculate for a finite set. So if your set is finite, here we go, with size n, with cardinality n, then the power set has cardinality 2 to the power of n. We're looking at the subsets of a finite set, and we are counting them. You saw an example of this before when we had a very small finite set, the set containing 0 and 1, and we listed all of the elements. We saw it before that with tricky example C of the set containing the empty set and the set containing the empty set, which I said had 4 subsets, and I asked you to go and write down the 2 that weren't on the screen. Here we go, there's a general rule here about powers of 2. The size of the power set is the power of the size, base 2. So we use induction because we've set everything up to work perfectly with induction. That's the nice thing about the natural numbers. For the initial step, we note that if the size of A is 0, then it's the empty set. So there's a single subset. Even the empty set has a subset. It's the empty set. If that's not obvious, try writing down a statement: if X is in the empty set, then X is in the empty set, and I hope you can see that's true. If silly. Anyway, it's got one subset. Silly or not, it's got a subset. So the size of the power set is 1. I suppose if I wanted to really spell that out, I would say that the power set of the empty set is the set containing the empty set. That's the set of all of the subsets. So the power set is not the empty set, there's something in there. Power set of the empty set minus the set containing the empty set. If I'm doing a set difference, I have to take away an actual set of elements. Okay, that would be the empty set, because I've taken away the only element. There's nothing that's in this power set and also in the empty set. So this has cardinality 0, so this has cardinality 1. That was a tortured explanation to say why I could go from single subset to this equals 1, but I wanted to demonstrate just what the definition looks like. But you have a set with one element in, and my definition says you can take away that element and have no elements. So you had size 1. I'm going to try and switch between this idea of how many elements you've got as a number and the cardinality, because those are, of course, the same thing. Right, suppose that for the inductive step in our proof by induction, n is now greater than or equal to 0, and that we've decided that the power set of S has 2 to the n elements. That's cardinality 2 to the n. And suppose that that's true for any set S with cardinality n. So my inductive, my statement here for induction is about all of the sets of size n, not just a particular set of size n, but all of the sets of size n. That's important. I should maybe have made that clearer at the start. Okay, a version of this statement for all sets with size n. It's kind of what's written up there, isn't it? Okay, so let A be any set with cardinality n plus 1. By the definition of cardinality, that means that there's an element A and a set which I'm going to call A prime. I don't mean the complement, I mean the set difference, A without that element. And by definition, that set, A prime, has cardinality n. If you like, that's why we're saying that this set has cardinality n plus 1. So I've got a special element A, not particularly special, but I've got an element A and a set A prime, such that after removing A, you've got n elements. Okay, I need to talk about the power set of A. And my plan is to split that up into subsets of A that contain the element A or don't. The 2 possibilities. That's where the number 2 comes from in this problem, I suppose. So we can partition this, which just means to split it up. We can split it up into a union between the power set of A prime, subsets of A prime. If you don't have A, then your subset is a subset of A prime. Or things that were almost a subset of A prime, except, they've also got this element A in. And the element A from that set difference is sort of a new element that's not in A prime. So these 2 sets, this one and this one, they're both sets of sets. I've got a description here of all of the subsets of A. Either they're subsets of A prime or they're almost subsets of A prime. They can include the element A. They're disjoint because the ones here in the first case don't contain A, and the ones in the second case do contain A. So these 2 sets of subsets are disjoint, and each of them has cardinality 2 to the n by the inductive hypothesis. Over here we're talking about the power set, and over here we're talking about a power set of A prime where I just do the same thing to every element of that power set. I union it with a set containing A, which I suppose importantly doesn't cause any of those subsets to be the same as each other. But other than A, they have to differ. I'm taking different elements of the power set of A prime. That's the inductive hypothesis that each of these has size 2 to the n and they're disjoint. So there's the use of the fact that I have the union between two disjoint sets. Its cardinality is all of these and all of those. I should subtract the intersection, but the intersection is empty. So I should subtract 0 from this line, I suppose. I have 2 to the n plus 2 to the n, 2 to the n that don't include a, and 2 to the n that do. Adding those gives me 2 to the n plus 1, which by induction means we're done. We started with the idea that any set of cardinality n has 2 to the n subsets, and we showed how to take those 2 to the n subsets and either throw in the element a or don't, and you'll get a subset of any larger set you were thinking about that also included a. So that's an inductive proof that the power set is of cardinality 2 to the n, where n is the number of elements of A. This idea about including or not including gives you an easier way to think about what's going on in the proof. So I've got this as an alternative, that you think about all of the elements of A and you make a yes-no decision about whether it's in the subset or not. You've got quite a lot of binary choices there, one for each element of A, which means you've got 2 to the cardinality of A, different combinations of choices, and different combinations of elements. And that gives you 2 to the power of cardinality of A, different subsets. That's a good thing to have in mind, that you were making lots of binary choices, and they lead to different outcomes. I think that this idea, if you write it out formally, turns back into the proof that we just looked at, because at some point you need to switch between talking about the number of elements versus the cardinality, but that's a really subtle distinction. The definition of cardinality that I've given you is not quite count the elements, it's about removing elements and seeing what you get. But that's a subtle distinction, perhaps. So I think this is good to have in mind. If you're trying to remember how big is the power set, then don't try to remember the proof I just showed you. Just remember that it's binary choices, and quite a lot of them. Okay, that's the power set of a finite set, answer 2 to the power of the size of A. For an infinite set, well, that's obviously not the answer for an infinite set. It's not going to be 2 to the power of infinity. But for an infinite set, you can still ask questions about the cardinality of the power set. In fact, that turns out to be an interesting question. You might be interested in whether it's the same cardinality as the infinite set. And of course, we can't answer that yet because I haven't shown you a definition of cardinality for infinite sets. But if you hang around for the chapter on functions, at the end of the chapter on functions, we'll be able to talk about a definition that uses functions between sets to try and work out whether or not they're the same size as each other. And that definition of same size will include infinite sets as well. There's an advert for a future chapter, but that is the end of this chapter. The next chapter is much shorter, and I'd like to tell you about relations between elements of sets. I'll see you for that one.